All right. So well testing is one of the procedures that the industry uses in order to determine the physical properties of the reservoirs after a certain period of production. They have to determine the skin, the permeability, and other properties like the initial reservoir pressure and so many other things. But those are the key ones that have to be determined. And generally, this well test analysis requires an organized procedure where they have to probably shut in the well for some certain amount of days before production can resume. After the analysis, production can resume. So one thing we have to realize is generally production takes place in the well. So what happens is as you're drawing fluid out of the well bore, there is a pressure disturbance that starts from the well bore and migrates gradually into the reservoir. And this pressure disturbance will migrate until it reaches the boundary. At that early stage of migration, that particular flow is dominated by the transient flow. I think I took them on Saturday to types of flow regime. We have the transient flow regime, the steady state, and the pseudo steady state flow regime. So at the early stage of that pressure disturbance, the flow that dominates there is a transient flow. So if we say the disturbance is generated from the well bore, then what we are saying is that the disturbance starts from the well bore and migrates gradually to the skin zone, because the skin zone will have to be the zone that is closest to the well bore, because the area around the well bore must have been damaged. We have already talked about the skin effect so many times. So it has to travel through that skin zone. Then beyond that skin zone, it travels now within the reservoir. And then when it now travels within the reservoir, it now reaches the boundary. So there are different types of measurements that can be used to interpret well test analysis. So we are going to group them into three stages. We call the early time response, which is that response due to the effects of the well ball and the region that is very close to the well ball, because that is where the wave, first of all, starts by traveling. It starts from the well ball, and then it starts traveling within the reservoir. So the early time response will be the response of the well ball, and then the response of the region that is very close to the well ball, which we call the skin, the damage zone, which we call the damage zone. Then beyond that zone, we have the mid-time response. The mid-time response now is when the pressure waves now is traveling within the reservoir, the actual reservoir. That's our mid-time response. Then when the pressure wave reaches the boundary, that is what we call the late-time response. You're going to see that a signal is generated in the reservoir. That's our reservoir, that's a well ball, and that's the reservoir. The signal is generated and the signal starts traveling both directions to the reservoir. Our early time response, the red wave is still around the well ball. The pressure wave is still around the well ball. Then for the mid-time, the pressure wave is now inside the reservoir. The pressure wave has now migrated inside the reservoir. Then for the late time response, we may have a ceiling fault around here, which is acting as Hello. Okay. So for the late time response, the pressure waves reaches the boundary, then if the boundary effect is now felt, So we talk of the oil well testing, because we have two types of air well testing. We have oil well testing and the gas well testing. So we have detailed reservoir information is essential to the petroleum engineer in order to analyze the current behavior and future performance of the reservoir. Pressure transfer testing is designed to provide the engineer with a quantitative analysis of reservoir properties. A transient test is essentially conducted by creating a pressure disturbance in the reservoir and recording the pressure response at the wellbore, that is bottom hole flowing pressure, as a function of time. So a signal is sent into the reservoir and a response is recorded. So the pressure transient analysis is basically made up of two measurements. That's what we need in order to carry out the well testing. We need pressure measurement and the time measurement. So we are measuring, once the production is taking place, we are measuring the bottom hole flowing pressure and we are recording the time. These two measurements now put together will be able to analyze the reservoir properties. So we are talking about the early time response. What can you use the information at the early part of that pressure measurement? What information can it give you? We can calculate the wellbore storage. The wellbore storage is the amount of fluid that is already inside the wellbore before production. So it may be, for example, a drawdown test, because there are two types of tests. We have a drawdown test where the well is shut down for a period of time, then it is allowed to reach static condition. Static condition is a condition where there is no pressure gradient that is created. Fluid cannot flow into the reservoir. At that point in time, now drawdown starts. As drawdown starts, there's already an amount of fluid that is inside our well bore. So as the fluid is being drawn out, at that early stage, the fluid is not yet being produced from the reservoir. The fluid that is produced at that early stage is a fluid that is inside the well bore. So it is only when the fluid must have been drawn down to a particular level, that's when the reservoir fluid now can start flowing inside the well bore. So we have the well bore storage at the early time. We have the skin effect. We have partial penetration. We may have a situation where the well is partially penetrated. That means our well bore has not completely penetrated through the entire reservoir. They may have drilled and ended somewhere in between the reservoir, in between that reservoir. So fluid is now flowing not only at the corners, but also at the bottom of the well bore. Fluid is also flowing inside the reservoir. So we may have a situation like it's partially penetrated. So we have, that's our reservoir. So we have partial penetration. Fluid is not only flowing in this direction, but it is also flowing in this direction into the well bore. So that is what we mean by partial penetration. We may also have conducted hydraulic fracturing. So they can use this now to analyze the effects of hydraulic fracturing. I will not go into hydraulic fracturing now because we are going to talk about it, I think in about week 10 or 11, we are going to talk about hydraulic fracturing. So I don't need to go into all of that. So in the meantime, the information that we can easily get is the permeability of the reservoir. But how does the reservoir behave? The reservoir can either be homogeneous or it could be heterogeneous. Homogeneous simply means that the properties is the same in all the directions. Heterogeneous means that the properties are changing in different directions. For heterogeneous, it may be dual porosity or it may be dual permeability. We don't want to go deeply into all of that. Then when we now get to the late time response, we may have a no flow boundary or a constant pressure boundary. We may have a no flow boundary, a situation where there is no way the fluid can actually flow, can actually cross that boundary. No amount of fluid can cross that boundary. But you may have a situation where that fault is not actually a sealing fault, that has so much so that the fluid can easily flow a little bit within the fault, but not that much. So, but in that particular case, it is not a no-flow boundary. So these are the various models, or these are the various things that we can characterize for a pressure transfer testing. So these are just the information that I've talked about. We have heterogeneous, we have dual porosity, we have dual permeability, we have composite. For when it reaches the boundary at the late time, we may have different types of boundary. We may have a leaky boundary, we may have a sealing fault, we may have a closed system, and so much and so much of it. So one of the best software that is used for pressure transfer analysis is Kappa-Cypher, that is used for pressure transfer analysis. But what we are going to do is we are not going to go into that for this internship. So what we are going to do is just to use Excel and see how we can determine some of these properties. So well bore storage is just what I've already explained, the amount of fluid that is found inside the well bore before the start of everything. So what are the various purposes? What's the purpose of well testing? At the exploration stage, you might use it to determine the reservoir size, the amount of hydrocarbon, the productivity of the system. At the development phase, which we have already explained about the various stages in the reservoir, in the production of hydrocarbon, we can talk of reservoir pressure, permeability, productivity, the damage, the drive mechanism, and all of that. Now, there are various types of well testing. There are various types of well testing. The first one we are going to look at is pressure drawdown. Drawdown simply means that you are doing production. You are doing production. So what you have to first of all do is shut in the well for a particular period of time so that you allow the well to reach static condition. You allow it to reach static condition where there is no fluid that is flowing. So during that period of time, the bottom hole pressure is not changing. It is constant. The bottom hole pressure is constant. So when you shut in that well, after that now you have to start flowing the well at constant rate. Remember, we are just moving from 0 rate to a particular rate. So you are now flowing it at constant rate. As you're flowing it at constant rate, the pressure, the bottom hole pressure is now reducing, So this is what we call pressure. This is drawdown. This is drawdown testing. This is drawdown testing. All right. For build up, what we are doing now is shutting down the reservoir, allowing the pressure inside the well bore to build up for some time. So what we will do is we will produce the well at constant rate. Remember that for drawdown, it starts with shut in before you start flowing at constant rate. For build up, it starts with producing at a constant rate, then you then shut down the well. The time that you use to produce at that constant rate is what we call our production time. That's our production time. Beyond the production time, we now have the shut-in time. So during the production, as you're producing at constant rate, the reservoir pressure is changing, but changing very slightly. When you now shut down the well, the bottom hole pressure is now building up because more and more fluid is leaving the reservoir and entering into the borehole, and then the pressure is now building up into the borehole. That's why we talk of pressure build up. All right. That's where we talk of pressure build up. So you have to bring out the relationship between flow rate and the bottom hole flowing pressure. Remember that in pressure transfer testing, the bottom hole flowing pressure varies, but the flow rate is kept constant. The flow rate is kept constant for each case, either for the build up testing or for the drawdown testing. All right, so we could also talk of injection drawdown. We talk of injection fault up. This is a situation where like we were talking of water flooding yesterday, where we have an injection well and we have a producing well. in one case, you may be injecting fluid inside the injection well, and it is now influencing the behavior in the producing well. And in another case, injection fall off, you stop the injection in the injection well, and then you observe the behavior in the producing well. So that's the injection and the injection fall out. Now, just don't bother yourself too much with what you're seeing there, because I know some of you, when you see formula, you tremble a lot. So we are not going to look at how all of this is proven. Trust me, even right at the level of masters, you will not see this proof. You will not see this proof. We did this proof at the level of PhD, at the PhD level. So, but this equation is the basic equation that is used for pressure transient analysis, what we call the diffusivity equation. It is a combination of three types of equation. We have the Darcy's law, a combination of the continuity equation, and another equation of state to show how the compressibility and the volume are changing as a result of change in pressure. So when you use all of these parameters put together, it now gives us this general equation, which we call the diffusivity equation. And this diffusivity equation is in the radial form. Remember, we are just assuming that most of our reservoirs are radial flow reservoirs. That means the fluid is flowing in all directions. So if we call this particular term here the diffusivity constant, then we are going to have the equation that is simplified in this manner. For steady state flow, remember, for steady state flow, we said the pressure of the reservoir does not change with time. The pressure does not change with time. In this particular case, dP on dt is 0. So all of this particular term becomes 0. I have said let's not bother ourselves. It's just to know that the basic equation that is used for well test analysis is the diffusivity equation. This equation is not easy for you to solve. For you to solve this equation, there are two things that you have to first of all characterize before you solve this equation. First is the initial condition. And the initial condition is the reservoir is at a uniform pressure when production begins. So we are assuming that at the early stage of production, reservoir is at a uniform pressure. If that assumption is not made, then there is no way you can solve this equation. Another assumption is the boundary condition. We are assuming that the reservoir is elastic. That means it is infinite acting. That means there is no, the pressure disturbance has not yet reached the boundary. That's why we are talking of RE equal to infinity. So the production is not feeling the effect of the boundary. It's not feeling the effect of the boundary. If these two conditions are met, this equation now can be solved. And in this case, we can talk of constant terminal pressure solution or the constant terminal rate solution. Remember, our interest is on constant terminal rate solution because we are talking about constant rate. That is where pressure transient analysis is. That's where our well testing is. They can either call it well testing or pressure transient analysis. It's still the same thing because we are analyzing the pressure effects in the transient flow period. Because remember, I said during the early stage of production, the flow is mostly transient because the boundary has not been felt. It is only when the boundary has been felt when we cannot talk of steady state or pseudo-steady state. In this case, we can talk of E-function solution or the dimensionless pressure drop solution. We are not going to lay our emphasis on the dimensionless pressure drop solution. We are going to talk about the E-function solution. So for the E-function solution, when this equation is solved, it gives us this particular equation, which we call the E-function solution of the diffusivity equation. It gives us this particular equation. We are not going to bother ourselves so much on the equation. That's a general equation of it, but we are going to use the simplified form. We are going to use the simplified form of the equation. This is a minute of integral. This is the minute of that integral, this exponential integral that we have. If we have the exponential integral of negative x, it is approximately equal to this. They can also approximate it to this, but our interest is not on that. This is the generalized form of the diffusivity equation, which is what we are going to use today to do our analysis. So if this is the general form of diffusivity equation, it means that if our variables are pressure and time, remember we are measuring the bottom hole pressure and time. So all of these other parameters are constant. So if I draw a graph of P against log T, if I draw a graph of P against log T, I expect that it should give me a straight line. If it gives me a straight line, then the gradient, remember if I have an equation in the form y equals mx plus c, we should already know this straight line equation. If I draw a graph of y against x, anything that is attached to x becomes my gradient. So if I draw a graph of p against log t, forget about all these other terms, they are constant, so we don't affect the equation that much. It means that the gradient of the graph is going to give me this parameter. It's going to give me this parameter. If I know my flow rate, my formation volume factor, my viscosity, and the thickness of the reservoir, I can use that to calculate the permeability of that particular reservoir. I can calculate the permeability of that particular reservoir. I want to take this off so that it will not distract us subsequently. All right. So let's look at now the Horner's plot. Horner's is just someone that came out with a better way of how we can use this pressure transient testing in order to analyze the reservoir to get the reservoir properties. For drawdown, he said, just what I'm just explaining. He said, if you take this particular equation and rearrange this equation, you are going to have this format. Remember, we can use the laws of logarithmic to separate this particular term. If you use the laws of logarithmic to separate this term, you have these two terms. Remember, we always have a law that says that log AB is the same as log A plus log B. So if I separate it, it will give me these two terms. If I draw a graph of P against log T, it gives me a straight line, and the gradient of that straight line is going to be equal to this particular term. And if I now this is what they have just explained here. PWF is equal to A plus M log T. So all of this particular parameter becomes our M. It becomes our M. All right. Now, if I draw that, I am seeing my value of K. If I say M is equal to all of these parameter, I can make K the subject of that equation, and it will give me this particular parameter. And also, we can calculate the skin of that particular reservoir. What is the skin factor of that particular reservoir? It uses this formula. P1R is the pressure of 1 hour. That means what we have to do is to go to where the time is 1 hour. We extrapolate wherever we meet this our straight line. Remember, at the early stage, it doesn't start, the flow does not start from the reservoir. The pressure disturbance starts from the boundary before it gets into the reservoir. So at our early stage, we don't expect it to be a straight line. And at our late time stage, the pressure is now, the flow is now being affected by the effects of the boundary. So we don't expect it to be a straight line. So we are expecting straight line only at the mid-time response, only at the mid-time. That's when we expect the straight line. And that is the straight line that we are going to use to calculate the permeability of the reservoir. But we expect all of this because at the earliest time, we have talked about wear ball storage and the skin effect. At the late time, we have talked about the effects of the boundary. So we'll use our straight line at the mid-time. That's when we talk of transient flow region. That's our transient flow region. Okay, for a build-up test, remember for a build-up test, we have to For a build-up test, we have to flow the reservoir for a certain period of time. That means we have our time, our production time. Then beyond the production time, now we have our shut-in time. So for a build-up test, we are drawing it against what we call the Horner's time, the log of the Horner's time, not just the time, but the Horner's time. So we have our production time plus our shut-in time divided by our shut-in time before we take the log of that particular value. Then our P1R will just be to take 1 hour from 1 hour now, from P equals to 1, we take it right up, and wherever it meets this particular straight line, we read the pressure. That is the pressure at 1 hour. That's the pressure at for P1R that we can easily put inside the formula, this formula in order to calculate the skin. All right, so we are going to end there for the theoretical part. Let's go now to our Excel and see how we can apply this. This is our shut-in time, and this is the pressure. So they are taking it at particular periods of shut-in time at 0.167 seconds and all of that. They start measuring each time. So they have the equipment is already designed in such a way that it measures the pressure at particular time intervals that has been designed. They are telling us that the pressure build-up test was conducted on a well that has been producing at 300 stock tank barrel per day for 53 hours. So our pressure here is okay, it's already written there even. Our shut-in time in hours. So this pressure is in terms of hours. So this is our production time. So what we are first of all going to do is to calculate the Horner's time. The Horner's time is, let's insert the change in time, change in T, plus our production time, which we'll just call T, divided by the change in T. Divided by the change in T. That's our Horner's time that we want to calculate. If you look at what we have here, that's the Horner's time there. Production time plus our shut-in time divided by the shut-in time. So our production time there is 53. So we'll put it in bracket so that the software does not misunderstand our formula. Oh, we have to start with equality. We open our bracket, we have 53 plus our shut-in time. This is our shut-in time. Then we close the bracket, divided by our shut-in time again. We press enter, so that is our time. Then we take it down. All right. And it does the calculation for us. So that is our Horner's time. We want to draw a graph now of pressure against the log of Horner's time. Please, we will not waste energy calculating the log. You can always calculate, then at the tail end, let's make sure that nothing is highlighted. We can always plot, then at the tail end, we are plotting a scatter plot. We'll select our data. So we will just call it our build up test. We'll just call it our build up test. For the x-axis, we have our time. For the y-axis, we have our pressure. All right. So that's what we have. Then we are going to go to our x-axis. We can always add the scale. We can always add the title. We have seen how to do all of that. You can go now to your x-axis, highlight it. You take format axis. Then you come and you change it to logarithmic scale. You change it to logarithmic scale. Then you put the values in reverse order. So we are going to put the values in reverse order. When you put the values in reverse order, you can now see it in that form. When you put the values in reverse order, you can now see it in the form, in this particular form that you have there. So that is it in reverse order. I can still, let's highlight here. Let me see. Anyway, let's leave it like that. So this is our pressure axis. You add the scale, or let's just add, because some of you like that. To add these things will be a problem again. So we take this, that's our PWF, capital PWF. So we are going to highlight. So we change the size to about 20 so that we can see it there. Then yeah, it's our honors time. We'll just copy this. It doesn't paste. There's no paste there. All right, so you can type that. You can type that at your leisure time. All right. So this is our main interest. We have the graph in that shape that we want. So we want to identify our transient flow period. We want to identify our transient flow period. I could also reduce the scale of this. Maybe it goes right up there. Anyway, let's leave it like that. So we could now identify our transient flow period. We'll highlight this. We go to format. Then we take the straight line and we try to see if we can draw a straight line at that level. Let's change the color to red so that we can see it well. We change the size, very large size, like that, so that we can see it well. So we try to see how we can identify that straight line the best possible way. You see how we can identify that straight line up there the best possible way. All right, so that's our straight line. Now, how do we identify the gradient of the straight line? What we are going to do is to identify the start point and the end point of that straight line based on this data that we have. So if I put my point there, if I put my point here, I am seeing it at a pressure, a time of 11.6. 11.6, this is our 11.6, a time of 11.6. Then if I put it here, I'm seeing it at a time of 4.2. So it starts from 11.6 and ends at 4.6. That is all of these points on that straight line. All of this point is this and this. So I have to use all of this data now. That's what I have to use now to calculate the gradient of that straight line. So I'm going to take my M is equal to, remember we calculated this the other day, slope is equal to the talk of known Y's value. So I'm going to click on that. Oh, I don't need to click. I put the Y's value. We start from here. We take it to the end. Then I have comma. Then the known X values, I will take the log, because remember, here we have not included the log, but the graph is in log form. So I'm going to take the log of this, the log of all of these, and then I close this. Then I close the first bracket. I have to close this first bracket. What I've closed is this one. So I'm going to close it the second time again. And that is our gradient. That's the gradient of that particular graph, -9.7. So now that asks us to calculate the average reservoir pressure. The average reservoir pressure The average reservoir pressure is the pressure after 1 that P1R. That's what we mean by our average reservoir pressure. That P1R is our average reservoir pressure. So from what we are seeing here, we are just going to extend this graph. When we extend this graph right up to this point, we can read the pressure value at this particular point. We can read the pressure value at this particular point, and that is going to be our P1R, which is the average reservoir pressure. That's the average reservoir pressure. All right. The reason why they are calculating P1R is because we want to calculate the average reservoir pressure is a pressure at the start of the experiment when there was no flow taking place, that static condition. And if it is at the start, it means that our time is 0. And this time can only be 0 if this value is 1, because log 1 is equal to 0. Log 1 is equal to 0. So it means that our time here is 1, so that when we take log 1, it gives us a time of 0. That's the reason why they are taking P1R. That's why they are taking P1R. So from there now, our P1R, we can approximate it to 1,950. We can just approximate 1,950. That's our P1R. And then from there now, we can calculate our permeability. Our permeability is negative 162.6. So we are going to go to our. All right. So what I'll do is I'll just take snipping tool. I'll just screenshot this. I'll take these formulas so that we don't have to be coming back here again. And I copy it. I go now to Excel and I paste it somewhere there. So that's the formula that I'll be using. So our permeability K is equal to, we have negative, this negative will take care of this negative. So our overall answer is positive. So we don't need to put a negative there again. So I have 162.6 times, I put my star, times the flow rate, which was given at the beginning, 300. That's our flow rate, 300 times. We have our formation volume factor, which is 1.26, 1.29, it's 1.29. Yes, 1.29 times our viscosity, which is 0.85, divided by the gradient, which is 97.99784 times our H, the height of the reservoir. Has it been given? The height of the reservoir has not been given. So what we are going to calculate here, we'll leave the H there, and then we are going to push that. But what we are going to call here, this is not permeability, but it is permeability thickness. So this is KH. This is KH. So if you don't know the thickness of the reservoir, you are going to calculate permeability thickness, because if this H crosses, you have permeability thickness. Use this area to calculate the thickness of the reservoir, but we don't want to go into that complicated calculation. So we are going to calculate permeability thickness. So if you are using a software like Kappa Cypher, what it will give you is not the exact permeability, but permeability thickness. It can only give you the exact permeability if you are so sure of the thickness of the reservoir and you have calculated that particular parameter. So we can also calculate the skin. The skin is equal to, we have 1.151 into, we open our bracket. We just hope that this formula, you will accept it. Let's know, and then we put all of this first one in bracket first. We have bracket P1R, which we have calculated as 1950 minus P initial. P initial has not been given. Let's see. Okay, P initial is our initial pressure. That's the starting pressure, 1451. 1451.5. So I'm going to close the bracket. Then I divide this by M, which is the gradient. I'll just write it down because I don't want complication. Negative, let's put in bracket, negative 97.97.9784, and then I close it. All right, minus the log of K, which is yeah, we would have we need the permeability. So let's just assume a thickness. Let's just assume a thickness of 10 feet. Let's just assume a thickness of 10 feet. So I will come to this formula. Let's list that. I've started this formula. The equation wants that I should finish the formula before I go anywhere. All right, so please, let's just do an assumption. Let me just assume that the permeability is 150. I'm not saying it's 150. So let's just assume that the permeability is 150. So we have the log of if the thickness is 10, if we divide this by 10, we are going to have 54.6. So let's use it like that, 54.6 divided by, we have porosity, which is 10%, 0.1 times. We have our viscosity, which is 0.85 times. We have our compressibility, total compressibility. If I change this to decimals, it will give me 0. I will have 40, then 116. So times 0.000012 times the radius of the well bore square. The radius of the well bore has not been given. Oh, yeah. All right, so let's just assume it at 0.1. So if I take 0.1, I square it, it will give me 0.1. I square it, it gives me 0.01. And I now close that lock. I open it here, I've closed it there. Oh yeah, the formula is already, I'm not yet through. I want to shift this this thing now. The formula does not want to. All right, so let's just continue from there. All right, at the end of it, we have plus our 3.23, and then I close the bracket. Let me be sure I have closed this bracket. All right, yes. This lock, I open it here, I closed it here. This closing is for the first one. This one, I open it here, closed it here. All right. All right, so that's our thickness. That's our skin factor. Sorry, that's our skin factor. So it already tells us that there's a damage there. There's a damage there, and the damage factor is 2.7. Remember, if you go back to our nodal analysis day one, the free training I did, I took time to explain the skin effect. And I said if it was positive, it means that the well has been damaged. It means that they have to start thinking of how they have to treat that region around the well ball. So we have now used the well testing analysis in order to determine the permeability of the reservoir and to determine the skin factor of that particular reservoir. Generally, you have a software like Kappa Cypher. It will do everything for you. It will do everything for you, but you have to know how it is done. Because if you are writing a project on pressure transient analysis, you have to explain all of this in your methodology. The mistake most of us or most of you do in pressure writing is that you just feel that because the software is doing the calculation, you don't need to explain how it is done. No, the software may have given the skin factor, but people need to know which formula the software is using to get the skin factor. So you have to illustrate all of this in your methodology, and you take time to explain how you have to get to the final answer. So this is going to bring us to